My name's David Holmes. I'm the CTO for Energy at Dell Technologies. And today, perhaps slightly surprisingly, I'm not going to be talking about our products and solutions for high-performance computing in the oil and gas industry. Instead, I'm going to be talking about a subject that I think is going to become increasingly important to this community over the coming years. And that's the broader trends that are happening in the energy industry, and particularly when we think about the energy industry in the context of climate change and the energy transition towards a low carbon economy in the future. Start off by looking at the opportunities facing our industry. There's rapidly expanding demand for energy. We expect over 1 billion people to become material energy consumers over the next 10 years. That's the equivalent of adding North and South America to the power grid. We also see dramatic growth in renewable energy and the decentralization of generation, as there are increasing points of generating capacity across our electricity systems. But that generates some challenges. The rapidly expanding demand for energy is happening at a time where we need to dramatically reduce greenhouse gas emissions, working towards a goal of being net zero by 2050. That growth in renewable energy is great, and it's a good indicator of our progress on that journey through the energy transition, but it means a much greater proportion of our generating capacity is intermittent. And the decentralization of generation introduces lots of orders of magnitude more operational complexity in delivering and managing our energy systems. Let's try and visualize this. Let's go back 100 years in time to when the electric grid was first conceived. It was a relatively simple model. Electrons were generated on the left-hand side of this picture, and they traveled in one direction over to the right-hand side, through a transmission grid, a distribution grid, to substations where voltages were stepped down and then delivered to industry, offices, and homes. Well, what's been the transition? Well, over the last couple of decades, quite a number of things have happened. First of all, we saw the grid endpoints become producers and consumers of energy. Essentially, the grid became bidirectional, as energy could flow to energy consumers who could also be producers sending energy back onto the grid. We saw the introduction of distributed energy resources, utility scale generating capacity for solar, wind, geothermal, and other forms of distributed generating capacity, introducing increasing amounts of intermittent generating capacity. We've seen the rise of electric vehicles and the changes that they place in terms of the load on the grid. We've seen community solar projects as individual communities look to move towards low carbon forms of generation. Now, to meet the challenges created by this intermittent generating capacity, we're starting to add large amounts of utility scale energy storage. In Texas, for example, we're expecting 2 to 3 gigawatts of storage capacity to be added to the grid in the next couple of years. And to help manage all of this, we need the introduction of a new generation of grid automation systems that help deal with these orders of magnitude more complexity in our energy systems. And this process we call grid modernization. And it's probably the greatest change that's going to happen to the energy industry in our generation. We predict that approximately $15 trillion is going to be invested in grid modernization over the next 10 years. That includes the addition of 16 million kilometers of new transmission and distribution power lines. It includes hundreds of billions of dollars a year being invested in the digitalization of the energy systems which we've relied upon and which have been roughly the same and analog based for decades. And for anybody here who's ever worked with operational technology, You'll know the complexity of bringing together new IT systems together with established operations technology. And I'm sure you also will realize that what we're talking about is critical infrastructure. It's heavily regulated, and there are numerous regulatory standards that must be complied with in the delivery of these new systems. And there's a new set of vendors, software vendors from the ones we're perhaps used to working with, who are building this new class, this new generation of digital systems for the new modernized electric grid. So what about the role of high performance computing in the energy transition? Well, there are a couple of dimensions to this. One is, as HPC practitioners, we need to think about our role in the use of energy in delivering these critical computational capabilities. The picture here is of ENI's HPC-5 supercomputer, which they assess to be one of the greenest supercomputers on the planet, based on its watts per petaflop delivered, and also based on the large solar array that helps to power this system. And we need to think about, when we're designing HPC systems, how we continue to drive new levels of efficiency in these systems. It's an area that we spend a lot of time thinking about at our AI and HPC labs in Round Rock. And certainly an area that if anybody's interested in, we'd be more than happy to discuss in more detail. But perhaps more importantly than just thinking about the way in which we operate our high performance computing systems and how they're powered, we need to think about the application of them. One of the key applications that ENI are using HPC-5 for is in the research of sustainable energy. Now, when I think about the traditional HPC workloads in oil and gas, I tend to roughly classify them in three different classes of workloads: processing, simulation, and artificial intelligence. They're all, to some extent or another, high performance computing problems. This community has the skills to build, operate, and optimize, but they're slightly different classes of problems. They typically require different computational approaches. They require different scales of computational capacity, and they work with different data sets. What's interesting is if you start investigating the broader energy market, you'll see some parallels between what we've traditionally done in oil and gas and some of the HPC workloads out in the broader energy industry. There's a huge amount of processing that's required to do things like computational fluid dynamics, to analyze the effectiveness of wind turbines. I must admit, I thought they were a straightforward piece of technology. If the wind blows hard, then you get lots of power. If the wind's not blowing at all, you get no power. But there are very complex nonlinear physics models that describe how to construct and how to optimize wind turbines. And we're seeing companies increasingly use high performance computing to increase the efficiency and the generating capacity of their installed base of wind turbines. Simulation is critical to being able to manage the future energy grid. Understanding how to predict what's going to happen with the grid based on a whole variety of new data sources is going to be critical to effective operations. Understanding, for example, how demand response can play a role in optimizing the consumption of energy. There are a number of energy workloads that are non-time critical. And so we need to understand through simulation how we can build and design grids that can take advantage of the capability to manage the time at which particular workloads are placed on the grid. And finally, artificial intelligence. The grid is going to become one of the greatest generators of data that we will come to see. Vast amounts of data being generated in real time from millions of locations, all of which has to be analyzed, processed, and automated decisions taken to effectively manage the delivery of energy to consumers. And this is huge amounts of data at the edge of the network that needs to be analyzed in the core of our network. And so we're going to see large computational AI systems building and delivering models that get distributed out to the edges of our networks. So I hope I've given you a glimpse and an insight into some of the things that we're seeing in the broader energy industry and the role that the high performance computing community can play in supporting energy companies as we go through this energy transition. If you'd like to find out more information, please do visit our website, delltechnologies.com/energy, where we have use cases and examples and where we talk a little bit more around our thinking on the energy transition, or you can snap this handy QR code. Thanks very much for your time and attention. I hope you enjoy the rest of the conference. Thanks and goodbye.